Yes, sir.
Okay, good. So I'll just start. So I'll be covering the first 4 chapters. So for this course, we have 2 parts. So the first part, the chapters are mostly on the linear algebra, which is the first 4 chapters, and the rest are the statistic is more on the statistic. Okay, so the statistic part will be covered by Dr. Izatu and Dr. Susanna. Okay, so I will be covering the first 4 chapters only. Okay, so the assessment, everything we will discuss in the tutorial group, not here. So this is just the math lecture. Okay, so I'll just start. So this is chapter 1, linear equation and matrices. Okay, so yeah, the outlines for this chapter. So the first sub point is the system of linear equations. After that is the matrix operations. So matrix operations are mostly you learned before, but we will just try to refresh back. Okay. And then the linear system in matrix form, also most of you already learned, either in matriculation or STPM or also in PRU. Okay, special matrices, partition matrices, and also non-singular matrices. Basically, this chapter is the easy one and nothing is very difficult about it. Okay, the first one is the linear equation. Okay, so linear equation, the definition is given by the equation 1. So the equation in the form of a1 x1 plus a2 x2 plus until an xn equals to b. This is called a linear equation where x1, x2, xn are unknowns, and then a1, a2, a3 until an. These are the real or complex constant, and then b is also a real or complex quantity. But mostly in our course, we only focus on the real number. Okay, the complex, we don't really focus so much on it. There could be question on it, but I doubt it. Okay, so normally we just deal on real number. And then a solution to equation 1 is a sequence of n numbers which satisfy equation 1 when 1 equals to S1 and then X2 equals to S2 and so on, Xn equals to Sn. So a solution is a sequence of n numbers, okay? N numbers. Meaning if you have n unknowns, so you see this is 1, X2 until Xn. So you have n numbers. So then in your solution, you must have n number for your solution. If it is less, then it will be less. For example, here, x1 equals to 2, x2 equals to 3, x3 equals to 4 is a solution to the linear equation 6x1 minus 3x2 plus 4x3 equals to negative 13. Okay, so meaning that if you replace x1 equals to 2 here, and then you replace x2 equals to 3 here, and x3 equals to negative 4. So if you do the arithmetic on the left hand side, you will get negative 13. So that's when we say x1, x2, x3 is a solution to this linear equation. If you cannot get negative 13, then this is not a solution. Okay. Now, if you have a system of linear equation, system here refers to a set of m linear equation, each in n unknowns. So if you have a set of linear equation like this, so each of these is a linear equation by itself. So if you have a set, then this is called a system of linear equation. So a solution to the system is a sequence of n numbers, which satisfy each of these equations in the system, meaning the solution must satisfy equation 1, equation 2, equation 3, and until the last equation. Otherwise, it is not a solution to the system. Okay. Now, if B1, B2, Bm equals to 0, then the equation 2 here is called the homogeneous system. Homogeneous means this part equals to 0. Okay. So for example here, so we have a system 4x1 minus x2 plus 3x3 equals to -1, and 3x1 plus x2 plus 9x3 equals to -4. So this set or this system of equation has a solution x1 equals to 1, x2 equals to 2, x3 equals to -1. So why we say that? Because if you substitute this value into equation 1 and equation 2, okay, meaning xy you replace with 1, and then x2 you replace with 2, and then x3 you replace with -1. Then for the first equation you will get -1, and then for the second equation you will get -4. So then this is a solution to the system of linear equation. However, x1 equals to 1, x2 equals to 8, and x3 equals to 1, this is not a solution because it's only satisfy the first equation, meaning this one. And it doesn't satisfy the second equation. So if we replace this one is 1, x2 equals to 8, and then x3 equals to 1. So obviously you have a 3 plus 8 plus 9. So this is not equals to -4. Okay. So then we can say that this is not a solution because it only satisfies the first equation, doesn't satisfy the second equation. Okay. Now next, any system of linear equation has either unique solution, no solution, and infinitely number of solution. Okay, unique means one solution. It only has one solution. Unique means one. Okay. No solution means you cannot find a solution. And infinite number of solution also means we can also say, normally we say many solution. Okay. Now a system of linear equation is said to be consistent if it has one or more solution, and inconsistent if it has no solution. So meaning here is this is consistent, this is also consistent system, and then this is inconsistent. Because it has no solution. So remember that for any system of linear equation, we have three cases, either one solution, no solution, or many solution. So if you draw the geometrical interpretation in 2D, okay, because if you look at our linear equation, so if you have two unknowns, in 2D means we only have two unknowns. So if two unknowns, basically the linear equation represent a straight line. Okay, so what does it mean by unique solution, no solution, and many solution in terms of geometrical representation? Okay, so let's say we have two linear equation. If unique solution, then we have one intersection point. So this is one intersection point. So this is the solution to the fourth linear equation. So in this case, we say this is unique. This is unique solution. And then the second one is that the first equation and the second equation is overlapping, meaning in the simplified form they are the same. So then meaning that the entire line here, all the points throughout the entire line are the solution. So that's why in this is many solution, because all the points in the line is the solution. And then for the third case, this is no solution because they don't intersect each other, they don't overlap each other, so there is no common point between these two lines. So we say that this is no solution. So for example here, we have this linear system. Okay, determine whether it has a unique solution, no solution, or infinitely many solutions. So the easiest way is you plot the graph for each equation. Because here we only have two unknowns, so we have x1, x2. So this is a equation of a straight line. So basically you can plot the line. It's either you plot the line manually or you can plot the line using any online graphic calculator. Okay, so if you plot the line manually, so let's say for the first equation, so we look at the first equation first. Okay, oh sorry, I forgot to record, so I need to record first. Let's see. Okay. This is already on recording, right? Okay. Okay, so we continue with this. If we plot it manually, then okay. So we look at the first equation. So this is our first equation. Okay, 2x1 plus x2 equals to 3. So we can rewrite this in terms of x2 equals to 3 minus 2x1. So basically, if you remember the equation of straight line, we normally write y equals to mx plus c, right? So this is the y-intercept. And then this is our slope. Okay, so the same thing here. So this is our slope, -2. And then this is y-intercept. Okay. So if x2 equals to 0, then if x2 equals to 0, then 2x1 equals to 3. So x1 equals to 3 over 2. So when x1 equals to 0, and then x2 equals to 3. So basically we have 2 points already. Then you can plot the straight line. Okay. Oops. Okay. So one of the lines is this. I can't remember which one. So see, our slope is -2. So meaning it will be x1. It will be this line. Okay. Okay. So this is our first line. Okay. Line 1. So the second line 2x1 minus x2 equals to 0. So if you rewrite this one is x2 equals to 2x1. So this is our slope. So there is no intersection here, one intercept here. So meaning this is our second line. Okay. Third line, so x1 minus 2x2 equals to 4. So if you rewrite x2 equals to x1 over 2 minus 2, so this is our y-intercept. This is half is the slope. Okay, so if you find 2 points, so this is our 2 points here. So it would be this line. So if you look at our graph here, so there is no one intersection point for all two lines. We have a intersection point between two lines, but there is no common intersection points for all three lines. So then we say that the system has no solution. Okay. So the next example, if we compare the system with the previous system, so the difference here is the second equation. Okay, this is the second equation. So to plot the graph for second equation, okay, so we rewrite the second equation. So x2 equals to 3 minus 2x1. So again, this is the slope, this is the y-intercept, and then you find 2 points for plotting the graph. So now, if you after plotting the graph, you can see that we have one common intersection point for all three lines here. So this is the only solution. So then we say that in this case, we have a unique solution. Okay. And then the third example, so we have 2x1 plus x2 equals to 3. Second one is 4x1 plus 2x2 equals to 6. Third equation is 6x1 plus 3x2 equals to 9. So if you divide this second equation by 2, then you will obtain the first equation. If you divide the third equation by 3, we will also get the first equation. So meaning all these three equations are the same. Okay. So if you plot the graph for the three equations, basically you only have one line only. So basically this is line 1, line 2, and line 3. So in this case, we say that this is infinitely many solutions, and then all the points here are the solution. Okay. Any questions so far? If you have any question, just ask. Okay. Just stop anytime. I will keep reading the messages as well. Okay. So this is the geometrical interpretation for 2D. So for 2D, we have two unknowns, x1, x2, can be x, can be y, can be t1, t2, doesn't matter, as long as we have two unknowns. So if we have three unknowns, so that means we can simplify all the equation. Yes, if it is many solution, you can just simplify and simplify. In the workflow, you show that you simplify, and then you get one equation only. Then it's a many solution. Okay. Now for the 3D, 3D normally the equation will involve I think, let's see. For 3D, if you plot the axis, so we have three unknowns, x, y, and z. Okay. So for 3D, normally I'll just explain the geometrical interpretation in 3D so that you see what it means by unique, many, and no solution. But for 3D, we don't ask you to plot the graph lah. So if needed, maybe you can find online graphic calculator to plot the graph. Unless you are CS student, in CS student, then for the second year, you will learn how to plot the 3D graph lah. Okay, so for the 3D or 3 dimension, so in 2 dimension, we have a line. Then in 3 dimension, we have a plane. Okay, so in 2D, if you have a line, then in 3D, we basically have a plane. Okay, so this is plane. So P1, P2, P3. So plane 1, plane 2, plane 3. In Malay, plane is SATA lah. Okay, so tiga SATA. Okay, so for unique solution, again, if you have 3 planes, we can only have one common intersection point. So like this. So this is unique solution. It doesn't matter how big is your plane. For all the 3 planes, you can only have one point, one intersection point. So then this is a unique solution. If many solution, like the second case, this is many solution, then we have one intersection line. Okay, so this is our solution. Here, this is our solution. Okay, and then for no solution, is this case no solution, no intersection, no overlapping among the 3 planes. Okay, so then this is no solution. Okay. Now next, solving a system of linear equation. Okay, so 2 linear systems are co-equivalent if they have a same solution set. So for example, here we have a 2 system. So these 2 systems are equivalent because they both have a same unique solution. X equals to 2, y equals to 1. Okay, so this is left for your homework. You go back and try. If x equals to 2, y equals to 1 in all the equation here, you will see that it will satisfy this. Okay, then if you have same solution, then these 2 linear systems are co-equivalent. Okay, next is the matrices. So what is the relationship between linear system of linear equation with matrix? Okay, we will talk about it in a later chapter. But first, this is the definition of a matrix. So basically, you know what is a matrix already from what you learned before in secondary and high school. Okay, so I'll just skip this one. Boleh ya? I skip ya. You know what is a matrix. You know what is the row. You know what is J. You know if M equals to N, then this is a square matrix of order N. Okay, and then A11, A22, and so on are the main diagonal. This one boleh ya? I won't then. Jangan cakap I don't teach later. Okay, for example here, let A be this matrix. So the size is 2 by 3 matrix. 2 is the row 1, row 2, and then 3 is the column, number of columns, C1, C2, C3. So A is 2 by 3 matrix, and then B is 3 by 3 matrix because we have 3 rows, 3 columns. So 3 by 3 means this is also known as the square matrix. This is a square matrix. C is a 2 by 2 matrix. This is a complex number. So this is also a square matrix. Okay. Now matrix addition, I think I'll just skip. You know how to do addition kan? Boleh ya? You tak boleh ketuk kepala. So matrix addition, you should know how. So I'll just skip. This is SPM standard already. And then the property of matrix addition. Okay, so A plus B is equals to B plus A, and then A plus bracket B plus C is also the same as bracket A plus B plus C. And then there's a unique M by N matrix O, which is the zero matrix. Zero matrix means everything is zero. Okay. Such that A plus O equals to A. So anything plus zero matrix equals to itself. And then for each M by N matrix A, there is a unique M by N matrix D such that A plus D equals to zero matrix. So we should write D equals to negative A, and this is called the negative of A. Okay, so simple. Okay. Scalar multiplication, also you know how to do the scalar multiplication. So for scalar multiplication, you just it's just like expansion, like you multiply the scalar here into all the entries in the matrix. Okay. So this is the example. Also, I'll just skip. Okay, for this example, so there are two ways. The first way is you multiply everything first, then you get this, and then you multiply this, and then you get the second one, and then you do addition, you get the answer. Another way is that if you look at the matrix, they are the same. So change the first. So if you look at the matrix here, they are the same. So basically, you can do factorization. So you factorize the matrix, and then this one is negative 2 plus 3. So then you have this. So negative 2 plus 3, you simplify, this is equals to 1. And 1 multiplied with the matrix is the matrix itself. Okay. So the properties of scalar multiplication. So if you have two real numbers R and S, and then matrix A and B of the appropriate sizes, then R multiply bracket SA is equivalent to bracket RS times A. Second one is bracket R plus S multiplied with A is equals to RA plus SA. Third one is R multiplied with matrix A plus matrix B equals to RA plus RB. Okay. And the last one is A times R times B is equals to R times AB, also equals to RA times B. Okay. Matrix subtraction. So this is the same as matrix addition. It's just that now we have a minus here. So the way you do it is the same. And then the transpose. Matrix transpose is the same. Basically, you interchange row and column, meaning row becomes column, column becomes row. Okay, it's you just need to remember one way. Row becomes column, columns become row. So given a matrix A, the transpose is this. Remember, row become column, row become column. That's it. You just interchange the rows and column. Okay, that's matrix transpose. Now this is a combination of a transpose and a matrix addition. Okay, so find B when B transpose is given this. Then use A from the previous example to show that A plus B transpose and A transpose plus B transpose are equal. Okay, so you given B transpose is this, find the original B. So again, you column become row, column become row. Okay, so this is our matrix B. So show that this is 2 equals. So basically you find the values for A plus B bracket transpose. Okay, so A plus B, you do the addition first. So this is the addition and then transpose. So this is the transpose for that. And then the second one is A transpose plus B transpose. So this is B transpose, and then this is our A transpose. So you do addition, you get the same answer. Okay, so the conclusion is that these are the same lah. So properties of transpose. So A transpose again, it will get back to the matrix A itself. This is what we show already. A plus B bracket transpose equals to A transpose plus B transpose. And then bracket A times B transpose is equals to B transpose times A transpose. So this one you need to be extra careful because the order is different. It's not A transpose B transpose, but it is B transpose A transpose. And then number 4, RA bracket transpose. So is equals to R times A transpose, meaning that the transpose does not have any effect on the scalar multiplication here. So that's why you get R times A transpose. And then next is the matrix multiplication. So this one I'll just explain a little bit because I think some of you still cannot do the matrix multiplication. So this is the formal formula for the matrix multiplication, but I doubt you will understand the formula, so I'll just explain. Now, given matrix A and matrix B, so find AB. So the size for matrix A, this is 2 by 3. And then the size for matrix B is 3 by 2. So find AB. Find AB. Now to find the matrix AB, first thing you need to remember is to make sure that this value and this value is the same. Otherwise, you cannot do the matrix multiplication. Okay, so since this is 3, this is 3, so confirm can do matrix multiplication. So how do we do? So the size for the matrix AB is this and this. So the size for matrix AB is 2 by 2. So basically we must have something here, 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 here. Okay. To find this value, the first entry here, what you do is you take the first row, multiply with the first column, and then you do the summation, the addition. When you do the product, the total summation is this value. So meaning 1 times -2, you get this, and then plus 2 times 2 times 4, 2 times 4, plus -1 times 2, you get this. And if you do the summation, you get 4. Okay, so that's the first entry. To get the second entry, it's the same second entry here. So this is row 1, second column. Okay, so what you do is you take the row 1, multiply with the second column. Okay, so same, 1 times 5 plus 2 times -3 plus -1 times 1. You get this. Okay, simplify, you get -2. And the third one, this one is row 2, first column. Okay, so you take the second row, multiply with the first column. Okay, so 3 times -2, and then plus 1 times 4 plus 4 times 2. Okay, and then the last one, this is second column, and this is the second row and second column. So basically, you take second column, second row, multiply with the second column. Okay, so 3 times 5, you get this, plus 1 times -3, you get this, plus 4 times 1, you get this. Simplify, you get 16. Okay, so that's the matrix multiplication. Okay, next. Let A is given by this matrix, B is given by this matrix. Compute 3, 2, and 3 of AB. Now, this is rather than computing the entire matrix, we only compute 1 and 3 of the matrix AB. Okay, so if matrix AB equals to matrix C, then the 3, 2, and 3 is C32, meaning how to find C32? Basically is you take row 3, multiply with second row. Okay, but in formula we need to write transpose because this is row. If you transpose become column, then you can do the multiplication. So basically it's 0 times 1 plus 1, it's 0 times 4 plus 1 times -1 plus -2 times 2, so you get -5. Okay, so this is a property of matrix multiplication. Okay, explanation. So this is about the sizes of a matrix. Now, if matrix A is an M by P matrix, and then B is a P by N matrix, then matrix A is an M by N matrix. Remember what I said just now, if you have a matrix A, so this is M by E, and then you have B, this is P by N. If you want to find AB, so your first thing you need to make sure that this is the same. Okay, if this is the same, then the size of the matrix AB is M by N. Is M by N. So this is the meaning of this statement. Now another thing is what about BA? What if we want to find BA? So if you want to find BA, then say we rewrite again so that it's easier to visualize. So B is P by N size, and then A is M by P. Okay, we want to find BA. Okay, so before do the matrix multiplication, first thing you need to check is this value. Now because we have N, we have M, so we don't know what are the values for N and M. So there are many situations you need to consider. So the first one, if M is not equals to N, if this is not the same, then you cannot find BA. Okay, if M equals to N, then you can find BA. So the size for BA is P by P. So it's P by P. If these two has the same value, otherwise no. While the size for AB is M by M. Okay. The second one, third one, and the fourth one is basically the same. If AB and BA are both of the same size, they may be equal, okay, and they may be unequal. Meaning, if they have the same size, like a square matrix, same size, then it is not necessarily BA equals to AB. It is not necessarily equal. So we will look at the example here. We have two matrices A and then B. If you find AB, AB is equals to this, and then BA equals to this. So in this case, AB is not equals to BA. Okay. So you need to remember that AB is not necessarily equals to BA. Okay. Now this example is to find the sizes like the one I explained just now. So it's not very difficult. Okay, so I'll just skip. Okay. Now these are the properties of matrix multiplication. So A times bracket B times C is equals to bracket A times B times C. Second one, A plus B bracket times C equals to A times C plus B times C. Third one, C times bracket A plus B equals to CA plus CB. Okay. So this is example of a matrix multiplication. Given A is this matrix, B is this matrix, and C is this matrix. Find A times B bracket times C and half the ABC bracket and then transpose. So the first one we look at bracket AB times C. Okay, so basically you do the matrix multiplication first for AB. So this is matrix multiplication for AB, and then this is C. Once you get AB, you multiply again with C, and then you get this. Okay. Now this is how we calculate manually, but now since you have a calculator, scientific calculator, I think you can compute the value straight away. So since we already calculate A, B, C, so for this case, then you can just divide by 2. Okay, you already obtained ABC just now, so now you multiply half. So basically divide by 2, you get this, and then you transpose, apply transpose, so row become column, row become column. So this is the answer. Okay, clear? Now next is the linear combination. This is a terminology, linear combination. I think this is new to you. Okay, so if you have a K matrices and you have a K real numbers, C1, C2, C3 until Ck, and then K matrices means A1, A2, A3 until Ak. Then the linear combination of A1, A2, A3, and Ak and this is given by this. So this is how you write in full. This is how you write in short form. So summation, CIAI, you learn from your discrete max what is the meaning of summation already. So I is from 1 to K. So in expansion or in full, we write C1A1 plus C2A2 plus C3A3 until CKAK. So basically, any form of this C times matrix and so on, this is called linear combination. For example here. So we have a real number times a matrix plus a real number times a matrix. So this is an example of a linear combination. Second one is this is a real number and then this is a raw matrix. Real number, raw matrix plus real number, raw matrix. This is also a linear combination. The sign here doesn't matter even though this is a minus. So in terms of the formula here, you can say that the value of C is minus 3 lah. Basically you have a plus here. Okay. So anything in this form is called a linear combination. You just need to remember that. Okay. Now, so what is the relationship between linear system and matrices? Okay. Now, a linear system, a system of linear equation, you can rewrite in the form of a matrix where AX equals to B. So A is this matrix, X is the matrix of the unknowns, and then B is the right hand side. So this is the matrix B, and then X is all the unknowns, X1, X2, X3 until Xn. And then the A11, A12, A and so on. These are the coefficient of the linear equation. So that's why we say that matrix A is called the coefficient matrix. Okay. And then this is the unknowns. This is the B. And then this is the coefficient matrix. Now another way we write a matrix to represent linear system is augmented matrix. Now augmented matrix is obtained by joining column B to matrix A. So basically you write a big matrix. So this is the matrix A and then this is B. Okay. So then you draw a line to separate it to show that this is B, this is A. Okay, this is B, this is A. It's a different. In short form, we like this is a matrix square bracket and then A slash B. If you write like this, then we know that this is an augmented matrix. Now example here. So write the following linear system in the form of AX equals to B and find the augmented matrix. Okay. So by letting A is the coefficient matrix. Now if you look at our system, so basically here this is 0, y. Okay. So then you have a -2, you take out all the coefficients. So this is row 1 is the coefficient for first equation. Row 2 is the coefficient for the second equation. Row 3 is the coefficient of the third equation. Okay. And then X are all the unknowns, X, Y, and Z. So you have this. And then B is the right hand side. Okay. So the augmented matrix, this is how you write the augmented matrix. You join this and this together. Okay. Now next is the special type of matrices. A square matrix, n by n is a square matrix, meaning square matrix. A square matrix is called a diagonal matrix. If Aij equals to 0 for I is not equals to Z, meaning only diagonal you have a value, the rest is 0. Okay. A scalar matrix is a diagonal matrix whose diagonal elements are equal. The identity matrix is the scalar matrix where the diagonal values are all 1 and the rest 0. So for example here, so you have a matrix A. So you have 1, 2, 3. So diagonal means this is the diagonal. This is the diagonal. And then don't confuse with this. this is not diagonal. Diagonal is this. Okay, don't confuse them. So if you look at the matrix, only the elements along the diagonal you have a values, the rest 0. So this is a diagonal matrix. First, it is a diagonal matrix. And then you check second, is the value all the same? This is 1, this is 2, this is 3, so it's not the same. So A is a diagonal matrix. And then this is not scalar matrix. And then this is not identity matrix. Okay, so because this is not 1, this is not 1. Okay, so for matrix B, again, only the diagonal has value and the rest 0. So this is a diagonal matrix. And then all the values are the same, 2, 2, 2. So this is a scalar matrix. But this is not 1. So this is not identity. Okay. Third one is, okay, so this is diagonal. 1, 1, 1, all the same. So this is scalar matrix. 1, 1, 1, this is also identity matrix. Okay. Now, another thing that you need to note is that the way we write the identity matrix is IN. Okay, IN. N is the size of the matrix. I3 means 3 by 3. I4 is 4 by 4. I2 is 2 by 2 matrix. Okay. Next is the power of matrix. Okay, suppose that A is a square matrix, then A to the power of P is A times A times A. You're repeating P times. Okay, you repeat P times. And then A power 0 is the identity matrix. Okay, IN. For the non-negative integers P and Q, A to the power of P times A to the power of Q. This is equals to A to the power of P plus Q. This is same as the indices, the one you learn in Form 4, MX in Form 4. And then second one is A to the power of P and then power with Q again. So then this is A to the power of P times Q. Okay. Again, A, B to the power of P is not equivalent to A to the power of P times B to the power of P. Okay, unless AB equals to BN. Okay, so for example here, so given A is a 2 by 2 matrix, compute A squared and A cubed. So A squared is A times A itself. So you do matrix multiplication, you get this. And then A cubed is A squared, you multiply with A again. So you take this, multiply with A again, you get A cubed. Okay, next is the triangular matrix. Okay, a square matrix is called upper triangular if Aij equals to 0 for I greater than 0. You need to remember that for upper triangular, anything below the diagonal are 0. So anything below the diagonal are 0. Okay, so remember this is our diagonal. Anything below the diagonal are 0, then this is called upper triangular matrix. A lower triangular matrix, anything above the diagonal are 0. So this is 0. Okay. And then symmetric and skew symmetric matrices. Okay, a matrix A with a real entries is called symmetric if A transpose equals to A. Okay, so if you look at the example here, given A, if you want to find A transpose, okay, sorry. If you want to find the A transpose, so remember our row become column 1, 2, 3, 2, 4, 5, then 3, 5, 6, 3, 5, 6. So if you compare both of them, they are the same. Okay, so then we can say that this is a symmetric matrix. A matrix A with real entry is called skew symmetric if A transpose equals to negative A. Okay, now for example, this is a given matrix B. So if you find B transpose, so row become matrix, So you have a negative 2, 0, negative 4, negative 3, 4, 0. Okay. So if you look at compare these two matrices, so P transpose is actually negative. So this is 2, 0, 4, and then this is 3, negative 4, 0. Okay, so this is negative B. Okay, so we obtain P transpose equals to negative B. So we say that B is a skew matrix. Okay. Next is another example. Determine if the matrix below is symmetric or skew matrix. Okay. Given A, this is A, so we find A transpose. So again, row become column. So insert 3, 2, 5, then 2, 1, 1.5. Negative 1, and then 3, negative 1, 1. Okay, so if you look at these two matrices, so A transpose is not equals to A. So this is not symmetric. Okay, and then for second one B, okay, we first find B transpose. Again, row become column, so 0, 1, 5, negative 1, 0, 4, negative 5, negative 4, 0. Okay, and then this is actually, if you factorize negative, you get 0, 1, 5. This is negative 1, negative 5, 0, negative 4, 4, 0. So this is getting B. So for the second equation, we get second question, we get B transpose equals to negative B. So this is a skew symmetric matrix. Okay. So far, okay. We almost finished already. Glenn?
Yep, sir. Everything is
Okay,
fine.
sir. Okay, no problem.
Okay, next is the submatrix. So submatrix is obtained by crossing out some rows or columns of matrix A. For example, we are given matrix A. So if you cross out the second row and third column, you cross out second row and third column. Okay, so we get a submatrix. So what's left is You compare 4, -3. So this is a submatrix. Good. Okay. So partition matrix. Now, matrix can be partitioned into submatrices by drawing horizontal lines and vertical lines between columns called block of A. Okay, for example, so this is basically useful for a very big matrix. Okay, especially when you do programming, if you define your matrix to be a very big, sometimes it will slow down the computation. So it will be easier if you partition the matrix and then meaning you make the big matrix smaller and then you do your operation. For example, here we have this is a 4 by 5 matrix. So if you divide this, so this is one partition A11 and then this is another partition A12 and so on. Same thing for B, matrix B, okay. So the symbol here doesn't matter, it's just how you define your partition matrix. Next is the non-singular matrices, okay. So non-singular matrices, basically we deal with the inverse matrix, okay. A square matrix is called non-singular or invertible if there exists a matrix B such that A times B equals to B times A equals to identity, where B is called the inverse of A. Otherwise, A is called singular or non-invertible. Okay, meaning, what is the meaning here is that if you can find an inverse matrix B, then matrix A is called non-singular or invertible. You need to remember this. If you cannot find inverse matrix, then A is called singular and non-invertible. That's the meaning. So you need to be careful with singular and non-singular, invertible and non-invertible. They are a bit, sometimes a bit confusing for you. And then another thing you need to remember is that if a matrix multiply with the inverse, you will get the identity matrix. Okay, that's it lah. To verify that B is an inverse of A, what you need to do is you do this A times B equals to I. I here is the identities. So okay, as I said, a matrix A, if you multiply with its inverse, you will get the identity matrix. Now, for example, here, given matrix A, matrix B, so if you do matrix multiplication AB, okay, so 2 times -1 is -2. Delete this first. 2 times -1 is -2. And then plus 3 times 1 is 3, okay. And then 2 times this, you get 3. 2 times and then 3 times -1, this is a -3. And then 2 times -1, you get -2 plus 2. And then 2 times this, you get 3 minus 2. Okay. So simplify, this is 1, this is 0, this is 0, this is 1. So this is identity matrix. Okay. So since AB equals to identity matrix, then we conclude that B is an inverse of A. Okay. So this is how you verify that B is the inverse of A. So non-singular matrix, this is the theorem for the non-singular matrices. Okay, so If there is a inverse matrix, then it is unique. Meaning for any matrices, if you can find inverse matrix, there is only one inverse matrix. You cannot find two. And then if A and B are both non-singular matrices, then AB is non-singular. And then the inverse of AB is B inverse times A inverse. Okay, so this is for two matrices. You can also expand this theorem into many matrices, which is this. Then it is equal to this. So again, you need to be careful on the order. You look at the here, this is A1, A2, A3 until AR. So if you split this, it will begin with AR first, and then AR minus 1, and then A3, A2, A1 inverse. Okay. So the inverse of an inverse matrix is the matrix itself. So the inverse of A inverse is A itself. And the last one, if A is a non-singular matrix, then AT is non-singular, and then the transpose of the A inverse is the inverse of A transpose. Okay, so these are the few things that you need to remember, just in case it will come out in the MCQ later on. Okay, so that's it for the lecture. Any question that you would like to ask? So if no, then I'll stop sharing this. I will share the QR code again. If you have not scanned, then you wait a while. If you already scanned, then you can leave. Thank you, and see you next week. Take care.
Thank you, sir. Bye.
And bye.
Thank you, sir.